as well. And we are recording this session. And with that, I will turn it over to the workshop leaders and we'll help moderate the questions that come through Slack and the chat. So either Jacob or Adam or Amit, please take it away, or Jacob.
Yep, that's me.
Excellent.
Let me just mute my notifications as well. I don't want any interruptions. Yeah, so thank you very much for that introduction. My name is Jacob Tomlinson. I'm one of the Dask maintainers. I focus a lot on the deployment tooling within Dask, right? So Dask distributed and the kind of supporting packages that go around with that. I must apologize. I managed to lose my voice again. This happened at last year's Dask Summit as well. I don't know what's going on. I must be allergic to the Dask Summit. But I'm gonna try and go through things as normally as possible, but I just apologize for the croaky voice. So we're going to start off this session. I'm going to do kind of like a 15-minute introduction to Dask distributed and how you kind of run things at a reasonably low level. I'm then going to move on and give a talk about Dask Kubernetes, right? The intention was to have a bunch of different folks, but I ended up doing a couple. So apologies, you got to listen to me 2 in a row. I'm then going to get Anderson to give us a short plug for the HPC workshop that's tomorrow. I was originally I wanted to cover all the different deployment methods, and I kind of scheduled it like, oh, I'm going to do an HPC section, and then looking at the schedule, there's a whole HPC workshop. So if you're interested in HPC stuff, that's great. I'm not going to waste any time here talking about that. You can go and check out that whole thing tomorrow. But Anderson will tell you more in a bit. Then after that, we have Brad from Google Cloud here to talk about running Dask on Hadoop with Yarn, using Dask Yarn. I'm going to be joined by my colleague Nanthini from NVIDIA, who's going to be talking about deploying onto various cloud platforms. I think specifically we're going to be focusing on Azure for the talk, but we have a package in Dask called Dask Cloud Provider that allows you to deploy onto a whole bunch of different cloud platforms. Our final talk is Amit and Adam, who are going to talk to you about QHub, which is a quant site open source tool for deploying like a multi-user team-based Dask and Jupyter setup. But again, I won't spoil too much about that. And then at the end, we're going to move over to the Gather Town and have a bit of like a panel discussion. So like there's little kind of like private zones, right? They're like multicolored zones. We'll get everybody into one of those zones and we can have a bit of like a chat and discussion. So if you've got any questions, speakers may have factored in some time for questions, but we'll probably save most of the discussion for the end and we'll shift over to Gather Town. So I'm going to get started talking about Dask distributed at high level. So Dask distributed at its core is a centralized scheduler, which can take in a task graph and distribute that to workers, which will then perform some operation for you. Right? Hopefully you're aware of this being at the Dask Summit. But what I wanted to do here is kind of like reel all the way back to like, what actually is the Dask scheduler and what are the workers and how do they kind of interact with each other? So when you as a user are doing something within Dask, you're probably using one of Dask's collection types, right? Maybe using data frames, maybe using Dask array, maybe you're directly creating Dask delayed objects and futures and that kind of stuff. That gets turned by Dask into a task graph, and that gets executed either by your local machine, or it can hand that graph off to the Dask scheduler, right? This is it's a pure Python package that you install kind of as like a separate package from Dask if you want to, that can you create a client to connect to that scheduler, and it will then hand off the work, right? So we have this kind of overview here where you think of the client at the top of this as your laptop, right? Or your workstation. You're doing some work, you're writing some Python code, you're building up these task graphs. You then need a scheduler to hand that work off to, and that scheduler needs workers that it can give out individual tasks to. Those workers will perform that operation, get the result of that, and keep it in memory, maybe hand it back to the client via the scheduler. Everything's kind of distributed in this fashion. Now, all of this works actually by using Cloud Pickle and pickling up objects within your environment, moving them around, shuffling bits of memory about. Now, these processes all have to communicate with each other, right? And the default way within Dask that this communication works is via TCP. So it's kind of like a lower level protocol where the client creates a TCP connection to the scheduler and can transfer information back and forth that way. The workers will connect to the scheduler and create a TCP connection. The scheduler can also then create connections back to the workers in order to have exchange of information in both directions. And the workers can also create connections directly to each other. So if they need to transfer memory from one to the other, that doesn't have to go through the scheduler, right? Things can hop around all over the place. Within like a network environment, this does mean that the client must always be able to speak to the scheduler. So whatever firewall rules you've got set up, you need that connection to be established. And then the scheduler and all of the workers must all be able to connect to each other in either direction, right? So there's just something to bear in mind when you are deploying on various infrastructures. There needs to be kind of no restrictive rules. The scheduler tends to run on like a specific port. The workers will use kind of random high ports for their kind of listening servers, and they will need to be able to connect to each other on those ports. Now, Dask also has support these days for more interesting protocols as well as TCP. So if you have some kind of interesting network infrastructure, maybe you have like an InfiniBand network, or maybe you're using GPUs which are connected via NVLink, you can use UCX, right, which is like another protocol. You use it exactly the same as TCP. You just do UCX : / and your IP address. But UCX can upgrade your network connection based on, it will inspect what setup you have and then say, oh, there's actually an InfiniBand connection between these two machines, and that's going to be much faster than a TCP Ethernet connection. So I'm going to upgrade to using InfiniBand, and things will go faster. That's really great. It's a pretty reasonably new feature, but you can kind of play around with that on HPC systems. And the most recent addition to these protocols is WebSockets. So instead of having to create a TCP connection, which is something that's tricky to like proxy, if you want to sit your Dask cluster behind a reverse proxy or some kind of like layer 7 load balancer, TCP can be a bit tricky to route based on like a domain name or something you might do in that setup. So we also now have WebSocket support. So all of the comms can run via like a high level HTTP WebSocket connection, which means you can sit it behind, I don't know, Nginx or HA proxy or something for doing that kind of thing. But I just kind of wanted to mention that these different protocols are out there. We're mainly going to be focusing on TCP for probably the bulk of this workshop. Now, starting a scheduler in its very most basic form, if you've done a pip install Dask or a conda install Dask and distributed, you'll have the Dask and distributor packages, and they come with a bunch of command line utilities. And one of those is Dask scheduler, right? So you can just go to your bash prompt, you can type in Dask scheduler, and a scheduler will start, right? This is a Python process. This is just using console entry points. It will run the scheduler application from the Dask package, and it will start listening for Dask communication connections by default on port 8786, and it'll also display the Dask dashboard on port 8787. Now, this scheduler can't do a huge amount on its own, but we're at the very first point now, right? On your machine, you run Dask scheduler, you get a scheduler. Now, if I want to actually be able to perform some work, I'm going to need at least a worker that's going to be able to take tasks and do the work and hand results back to the scheduler. So we can create one of those by running the Dask worker command line utility. And we have to pass it that address from the scheduler, right? So we can see in the scheduler is running on this 8786. This is just on my, this is an example on my local LAN, right? But we pass that 8786 address to the Dask worker, and that creates a connection to the Dask scheduler. As I said, the Dask scheduler, the worker will start its own server on its own port. You can see here there's like a random port of 55333, and there's 55336. There's a few things going on. The Dask workers also have their own dashboards and things. So this will start up. It will connect to the scheduler. It will say, hi, I'm a new worker. I would like to register. Here's my IP address and port where I'm running. And the worker can then create connections back in that other direction. The worker will, by default, just try and work out, what is this machine? How big is it? What can I grab? So this is on my, laptop. It's a, 12-core Intel processor with 16 gig of RAM. So the workers just grabbed all of that and said, right, this is the resource that I have available. I'm going to connect to the scheduler. This is now part of the Dask cluster. The last piece of this puzzle now is we need to actually give some work to this cluster. And we do this by creating a Dask client. So within a Python session, right, within IPython in this example, I can, from Dask distributed, import the Dask client, and I can connect that client. Oh, I'm getting a bit of feedback on someone. Is there, Gabriel, could you mute, please? That's perfect, thank you. So you can give that same address, right? This is the same address we gave to the worker, that the client can connect to the scheduler on that address. Now, by creating this client object within your Python scope, Dask knows that's where I need to hand my work off to now. So before we created the Dask client, if we did any Dask work, this would run locally on my machine using the kind of standard threaded scheduler that's built into Dask. But by creating this client object explicitly, Dask knows, oh, I need to hand this work off somewhere else. I've got this open TCP connection to the scheduler. I'm going to start handing graphs down there, and that scheduler is going to get the workers to do this work for me. And we can find out information about this cluster. We can just have a look at the repro of the client object, and we can see it's connected to that machine. It's got the 12 cores and 16 gig of RAM from my machine. So we've got a small, minimal Dask cluster here. And I can throw work to it, right? I can import Dask array and make some big random array and, I don't know, do some stuff to it. And then when I try and persist that object, right, I'm basically saying to the Dask workers, please persist this object in memory, actually do the calculation and store the result in memory. That Dask graph will get handed to the scheduler. The scheduler will hand individual tasks to the worker. The worker will perform those tasks and they will hold that memory. So all of this is kind of working through that chain. You can set this up on your local machine. You can kind of play around with this and experiment and see how these individual pieces work. Now, in order to really get a view on what's going on, you can use the Dask dashboard. So I think way back on the starting a scheduler page, we had this other port, this 8787, right? This is where the Dask dashboard is. You can open this page in your web browser and you'll see a dashboard much like this. There's a whole bunch of different pages in here that give you some insight into what that scheduler is doing. The main status page here shows how much memory is being stored on the workers, how many tasks are being processed, a stream of what tasks are being performed by each core of the worker, and some overall progress bars, right? You can drill down into the workers, you can drill down into the tasks, you can look at the graphs. There's a really useful profile plot where you can see which sections of your code are taking the most time. All of this is being managed within that scheduler process, right, that we started on our command line at the beginning. Now, if you're a JupyterLab user, there's also a JupyterLab extension for Dask. If you search for Dask Lab extension, you'll find that. And it uses the same dashboard here, but we provide all of the same plots that we have in the dashboard as kind of individual pages. And JupyterLab can display those as separate tabs. So you can kind of pop out, you pop up in the left-hand side, there's a URL there. That finds the dashboard. And then you can click those orange buttons and it creates those different plots as tabs within JupyterLab. You can kind of drag those around and resize them. So you can see much of the same information here, the task stream and the memory used and that kind of stuff from the Dask dashboard. But we also have the graph from the graph page. That's what you can kind of see what you want to see into what your cluster's doing. You can do all of this without any kind of fancy deployment, just by running, installing JupyterLab, installing the lab extension, installing Dask, and then just running these Dask scheduler, Dask worker, connect to client, do some work, kind of get this all going on your local machine. It's a great way to kind of get to grips with what is going on within a Dask cluster and start thinking about what infrastructure and resources you have available to you that you might want to start reaching into. So to try and simplify this process without you having to get into all of this kind of nitty-gritty detail that I've just described, we have this concept of cluster managers. These are classes that we have implemented within the distributor project and also many of the kind of sister projects within Dask. It's a class that represents all of these processes, and it starts them and creates them and manages them for you. And it just simplifies this whole thing down. So instead of going to my command line and running Dask scheduler and Dask worker, I could instead in Python import the local cluster manager and instantiate that object. I just want to say cluster equals local cluster. And what local cluster will do is it will look at my machine, it will work out how much resource there is, and then it will start a sub-process for the scheduler. It will start sub-processes for the workers. It actually tries to carve up your CPU into like smaller, more manageable chunks. Sometimes if you just have like one worker with lots of threads, that's less efficient than if you have a few workers with a few threads. So the local cluster will kind of carve up large CPUs into smaller pieces. I think on my machine, I get 4 workers with 3 threads each or something. It starts these sub-processes, it starts the scheduler, and it gives me this object that kind of represents that. I can then create my client object again, but instead of having to worry about what that IP address was and what the port was that got assigned, I can just give the client that cluster object instead of a string URL. So when I just do this, I get the same client that I had before. I can send work through to the cluster as I did before, but I've not had to worry too much about networking or anything like that, right? I've made a cluster object, I've connected a client to it, and I'm ready to do my work. This is great if you have like a large workstation or something where you want to really make good utilization of all of the cores and threads on your CPU. Now, these cluster manager objects also have some kind of useful features, some useful utility methods that you can call on them. One particularly useful one is get logs. And this gets all of the logs back from the scheduler and all of the workers within your cluster. By default, it gives you like a dictionary of all of these. But if you're looking at things in JupyterLab, it actually can give you a nice like HTML representation where you have these little drop downs, you click the little triangles and it displays the logs for you. So if you're trying to debug something or troubleshoot what's going on in your Dask cluster, this is a great way of getting those logs back without having to worry about how did these processes start, how did things get created, where a log file stored on my system or whatever. Another useful thing that you can do with cluster managers, which makes less sense in what we're doing right now, but will make more sense as we go through other topics in this workshop, is you can scale your cluster. So we either have a scale method where you say the number of workers that you want to have within the cluster, or you have an adapt method where you basically say to Dask, you figure out how many workers you need as I give you graphs. If I give you a small graph, you might not need that many. And if I give you a big graph, you might want more. And you can give it like upper and lower bounds. It's always good, I find, to have at least one worker because Dask starts running tasks and timing how long things take in order to calculate how many workers you have. So if you have at least one worker, then you're able to do that profiling out of the box. And that makes less sense when you're using local cluster on your local laptop because you can't say scale 10 and get 10 laptops. But when you start moving onto cloud platforms or HPC platforms where you can requisition additional resources, this starts making a little bit more sense. But I guess what I'm trying to say is that these cluster manager objects are consistent in their API, right? When you have a cluster manager, they always have this get logs method, they always have the scale method, they always have the adapt method. There's utilities in here that should be consistent as you move around, especially if you're on different infrastructures. So how can I get more resource than my one machine? Well, before we dig into fancy approaches like the cloud, you could just SSH onto a bunch of machines and start the Dask scheduler and the Dask worker processes and kind of connect them to each other. I must admit, in a previous job, I used to do this on colleagues' desktops when they were at lunch in order to build little like pseudo clusters for doing things, right? You can just SSH in, you start the processes, everything's great. We actually have a cluster manager in Dask for this called SSH cluster. So instead of having to SSH into each one and remember which host is which and everything, I can just call SSH cluster, give it a list of host names. I have to be able to SSH into those host names without passwords or anything, right? I need to have SSH keys set up and everything. But this SSH cluster will manage all these connections for me. I can pass that to the client and the client will connect. I can create kind of small distributed clusters quickly and easily this way. So that's like a very quick overview of how these things work. But what we're going to do in this workshop is cover a whole different bunch of ways of deploying things, whether you're a cloud user, whether you have HPC resource that you have access to, whether you're using Kubernetes, whether you're a team or an individual. We're going to get into all sorts of stuff here. So thank you very much for listening to this first little section. As I said at the beginning, for those of you that may have joined partway through, we've got a few different talks now that's going to take this concept that I've just talked through of how Dask clusters are set up and kind of apply them to different platforms. So I'm afraid you've got to listen to my raspy voice for another 15 minutes, and I'm going to talk to you about Kubernetes. But then we've got Anderson, who's going to plug tomorrow's HPC workshop. Brad's then going to talk to us about Hadoop platforms. Nanthini is going to join me to talk about deploying onto the cloud. And Amit and Adam are going to talk to me about, join me to talk about multi-user deployments on Kubernetes. And then we'll have a panel discussion if you kind of have any thoughts about how you want to deploy things. So that's presentation one. Let's move to presentation two. So if you do have any questions from any of that, I'm afraid we're going to have to kind of save them to the end because we're reasonably tight on time in this workshop. So let me just take a breath for a second. Switch my brain over. One of the packages that I maintain within the Dask ecosystem is a package called Dask Kubernetes. We also have other Kubernetes related things. So what I wanted to do for this section of the workshop was kind of unpack how do various people deploy Dask onto Kubernetes, right? There's more than one way of doing this. Depends on your use case and who you are and what you're trying to achieve. So I'm going to try and unpack the different ways that we can do things. I'm not intending to do like a what is Kubernetes in this. Like if you are a Kubernetes user, I'm hoping to give you some useful information in here. For those that are not Kubernetes users, just think of it as you know, a scheduling system where I can ask for a resource and get it basically. So to give it like a slight bit more context about kind of what I'm talking about and where my brain's at when I'm explaining these things, I tend to think of there being two different types of Dask cluster. We have fixed clusters and we have ephemeral clusters. I'm a big fan of ephemeral clusters. But a fixed cluster is kind of maybe what you would more traditionally think of as like a compute cluster. If you come from the like Hadoop Spark world, this is probably pretty familiar to you. If you come from the HPC world, this is probably pretty familiar to you. This is kind of where you go through the effort of setting up some clustered scheduling system on some resource, and then you kind of leave it there and you feed it work and you share it between people, and maybe you have queues and all that kind of thing, right? You could definitely use Dask in this way, but there is another way of using Dask clusters as well. So the way that I often tend to use Dask clusters is by using ephemeral clusters. This is kind of where, as part of my work, I start a scheduler and some workers, I feed it a load of work, I maybe ask for more workers or fewer workers, depending on what my workload is doing, dynamically through that job. And then when I get to the end, I let go of all of that resource and it's gone again, right? It was just like an ephemeral thing. It's almost like it's a runtime, right? In order to just grab a bunch of resource, pull all these machines together, and make use of them. This is great if you can grab resource quickly. And Kubernetes often is deployed in a way where you can grab resource very quickly. This can be slightly trickier if you're on like an HPC system where queue times are quite long. You have to maybe think about things a bit more in advance, but it's still a great way of deploying things there too. So with those two cluster types in mind, the first Kubernetes deployment method I want to talk about is the Dask Helm chart. Now, this is a fixed cluster approach. If you're familiar with Kubernetes and Helm, Helm is a way of deploying like a pre-baked application, right? And it's kind of got all the pieces that you deploy onto Kubernetes. We have an official Dask Helm chart. You can add our Helm repo and pull down the latest release, and then you can just install Dask onto your Kubernetes cluster. Oh, that's a shame. Part of this slide isn't showing. Oh, well, that was strange. I've never seen that before in Google Slides. That was exciting. Right. Nothing seems to be missing. So the Dask Helm chart looks kind of roughly like this, right? We launch a Dask scheduler for you. We launch some Dask workers. We actually launch 3 unless you change the default configuration. And we also launch a Jupyter notebook kind of container. And they all get configured so they can all talk to each other and find each other. And we configure services and optionally ingresses as well. So you can get traffic in and see the Jupyter notebook, and you can see the Dask dashboard, and you can ignore the Jupyter server if you want and just use the Dask scheduler. But this stuff gets created for you within Kubernetes. It uses deployments to make sure that if nodes get destroyed or recycled, these resources will be recreated, and kind of everything's handled nicely within the scheduling system. Oh, don't do this to me. Okay, that's a real shame. Right, I'm gonna have to do this every time. I have no idea what's going on in Google Slides. Now this, as I said, this is a fixed cluster, right? So if the user disconnects, this cluster still exists. The user could come back later. They could reconnect. This cluster is immediately there for them to use. They can grab all of that resource again and do things. You can use Helm or Kube Control to add and remove workers by scaling that up and down, or they have to be very explicit about only doing that when there's nothing in worker memory and the workers are not busy, because Kubernetes doesn't care what Dask is up to. It will just add and remove workers kind of randomly. This is really useful, especially if you're running Kubernetes on some local resource. But it's worth bearing in mind when you go home at the end of the day, or you go on holiday, this cluster still exists. It's still taking up time. You've kind of like permanently scheduled this Dask cluster on your Kubernetes cluster. So the other approach to this is to create an ephemeral cluster, right? And Dask Kubernetes is a Python package that we have, which has a whole collection of kind of Kubernetes related tools. But within that, we have a cluster manager called kubecluster. This is a small Python library which speaks directly to the Kubernetes API and dynamically creates pods, creates the scheduler, creates workers from some kind of spec that you define. It can scale these things up and down. Kind of it allows Dask to scale these things up and down. So you're not relying on Kubernetes to add and remove pods and do things within the deployment. Dask itself is saying, I want to add more workers. I want to remove this specific worker, right? Memory is not lost. You can kind of dynamically scale as your jobs are running. And you do this by importing kubecluster from Dask Kubernetes. You instantiate it by passing it kind of like a pod spec. This is just kind of the definition for what you want your worker pods to look like. And then you can either manually scale that or adaptively scale that. And so this creates something a bit like this, right? You have your individual user, they're connecting into Kubernetes. They're directly talking to the scheduler and worker resources. One of the nice things here is we do create a service attached to the scheduler. And if that user could be themselves inside the Kubernetes cluster, right? If you have some other way of provisioning, maybe Jupyter, you might be launching from there. And so you can create connections directly within the Kubernetes cluster. It will speak to the service directly. That's great. Maybe you're exposing your service. Maybe you're kind of linking that service to your local network via a VPN or something. You can speak directly to that. But if your local machine can't figure out how to speak to the scheduler because you just haven't configured it, but you do have kubectl installed, that's great. It will just grab kubectl, use kubectl proxy, and create like a reverse tunnel to your local machine and connect that way. So it's actually quite a nice way, if you have access to Kubernetes, to launch some resource on Kubernetes without having to expose it to the outside world in any way. It will just make use of kubectl to do that for you. But the thing with ephemeral clusters is they're great if you want to just use them as you're doing your piece of work. But if that user disconnects, these resources were kind of being managed by their local laptop, by that kubecluster object that they'd created within their local Python session. So if the user goes, the cluster gets garbage collected and everything kind of gets wrapped up, which may be what you want. Often for me, that's what I'm after, but it may not be if you want to run something a bit more long running. Now, another package that we have, another cluster manager, that we have within Dask Kubernetes is Helm Cluster. Now, this is a cluster manager in every sense, like the other ones we've talked about, but this depends on you having installed the Helm chart that we talked about before already. So if you've come along, you've installed the Helm chart, you've got things up and running, you can instantiate this Helm cluster object from Dask Kubernetes, and you can tell it whatever you named the Helm release, and it will create like a representation of that Helm chart. And then you get the same interface you do with other cluster managers, right? You can call scale, you can call get logs, you can get everything back from your cluster that way. And it's just sometimes a bit more pleasant than using kubectl or Helm to scale your workers. You can use Helm cluster to do it. The same caveats apply in terms of Kubernetes not intelligently adding and removing workers, but it gives you a consistent way of dealing with things here. It also has the same utilities in terms of connecting to the service via proxying. So if you've Helm installed your cluster, but not done anything that's going to expose that service to you, you can make use of this Helm cluster manager to kind of reverse tunnel yourself into that Kubernetes cluster and connect through to Dask. All of this is documented at kubernetes.dask.org. So the last thing I kind of want to talk about here for the last few minutes is Dask Gateway. So Dask Gateway is like a centralized hub, which kind of does what these two things were doing combined, but it does it in like a centralized way. So what happens is you install a Helm chart, and that puts Dask Gateway and a proxy onto your Kubernetes cluster. And it also creates certain access controls so that gateway container can speak to Kubernetes itself and ask for more resource. So the user can then connect into Dask Gateway, authenticate with it, and then say, I would like a Dask cluster, please. And Dask Gateway speaks to Kubernetes, provisions a scheduler and workers, and kind of handles all the scaling and all the lifecycle for you. And it proxies your connection directly through to that Dask cluster. So it's kind of centrally managing that for you. This is great if you are in a team or there's a group of you, you have access to some resource, you have Kubernetes on it, and you don't want folks kind of everybody installing that Helm chart, and you don't want all this kind of chaotic pod creation from the ephemeral cluster. You want some kind of more controlled, centralized way of doing things. Dask Gateway can provide that for you. Using Dask Gateway looks a bit like this. If you pip or contra install Dask Gateway, you first have to create a connection to the gateway. So you import the gateway object and you instantiate that. You give it the address of the gateway service that's been created. So you may have set up an ingress or some kind of service for accessing that. And you have to authenticate with that as well. Dask Gateway supports Kerberos authentication. If you're running Jupyter Lab, it can hook into that kind of authentication. You authenticate with that, you get this gateway object, and then you can use that to list what clusters there are, get a specific cluster instance, scale it up and down, delete it, that kind of thing. But there's also a gateway cluster manager you can instantiate, and if you have a gateway object kind of in your namespace, it will use that gateway to create that gateway cluster. And again, it feels very much like the other cluster managers. You get the same utilities, the same methods for managing this cluster created this way. So Dask Gateway is great. Often it's used hand in hand with Jupyter, and I said it supports Jupyter authentication as well. So we do have another Helm chart within the Dask ecosystem, which takes Jupyter's Helm chart for deploying Jupyter Hub and the Dask Gateway Helm chart for deploying Dask Gateway, and it mushes them together with all the right configs so that things work. If my slides worked anyway. That's a shame. Sure, anyway, there we go. Right. Sorry about this. It mushes these two Helm charts together, and it deploys Jupyter Hub and Dask Gateway onto the cluster. You can authenticate with it. They can then ask for Jupyter servers and Dask clusters and all this kind of magic stuff. I tried to do lines on this diagram like my other diagrams to show what was talking to what, but just imagine lines everywhere. It got so messy I couldn't read what was going on. But you can put all of this inside. Everything's kind of managed for you. I'm kind of glad I didn't get too far into it, because we've got a talk later on in this session from Amit and Adam about how QHub is doing effectively this, right? It's Jupyter Hub plus Dask Gateway on Kubernetes. So I won't spoil their kind of topic as we go through that. So just to recap this Kubernetes talk, we have a Dask Helm chart, which allows you to just install a Dask cluster with a Jupyter notebook perpetually on your Kubernetes cluster. It's a great way to kind of experiment and play around. We have Dask Kubernetes, which in itself contains kubecluster, which is great for creating ad hoc ephemeral clusters kind of as and when you need them, for just grabbing a whole bunch of resource in a Kubernetes cluster for doing one specific piece of work. And then we have Dask Gateway, which is this centralized managed gateway for spawning clusters within Kubernetes on your behalf, managing them, managing their lifecycle. This is great for teams and organizations. So that's it. I'm kind of on time. I'm keen to keep the whole workshop going on time. I hope if you're interested in Kubernetes, it's been useful for you. I would now like to hand over, if my Zoom controls get out of the way, I'd like to hand over to Anderson, who's going to hopefully take over the screen share. You should be able to just take over the screen share and tell you a little bit about the HPC workshop that's going to be running tomorrow.
Sounds good. Give me a second. It's still, yeah, I don't have the controls.
You may need to
I think, yeah, unshare, yeah.
Zoom doesn't allow people to steal screen share.
Okay, let's try now. Okay. I think this should work now. Okay. Okay. So I assume you can actually see my screen. Okay. So yeah, so I have 5 minutes for this. So yeah, hi everyone. My name is Anderson Banihirwe, and I work as a software engineer at the National Center for Atmospheric Research. So as Jacob said, this is just a plug for tomorrow's workshop, which is going to focus on HPC and how Dask is basically used in HPC. And in that workshop, I'm going to give a talk on basically the current state of deploying Dask on HPC clusters. So we talk about like things like Dask job queue, Dask MPI. But then I guess for the 5 minutes that I have, I figured I would just give you a demo instead of just talking. Let me see if I can actually get Zoom. Okay, let's see if this works. Okay, too many windows. Okay, so basically, if you're not familiar with Dask job queue, so it builds on top of the spec cluster in Dask distributed. It provides pretty much the same functionality as any other cluster that subclasses spec cluster. So hopefully this shows up soon. Okay, good. So, Okay. So the way that you will use Dask job queue is by actually importing a cluster object that implements some custom logic for, because in HPC you have basically different HPC schedulers. So like you have things like PBS, Slurm, LSF. So Dask job queue implements classes for those different schedulers, and then you basically import that class. The things that you pass to that class, basically, some of them are kind of common, like whether you're using Slurm or PBS. Like in this case, we're specifying like how many processes we want in one block of workers. So we want one process, 2 calls, and then we're specifying the queue that we are submitting the job to, and then the wall time. And then you can also specify some other things that are actually specific to the cluster that you're working with. Again, what we're defining here is just like a configuration of jobs that are going to be submitting to the queue. So if you're using Jupyter Lab, you have the extension here that you can use to do the manual and adaptive scaling. So in this case, I can say, okay, give me 5 workers. And what Dask job queue is going to do under the hood is just submit a bunch of jobs. So we can actually take a look here. You see that it basically goes and actually submits 5 jobs because I specified that I wanted 1 job, one Dask worker in a single job. So the scheduler, so in this case, PBS gives me back 5 running jobs. And we can actually look at the script that Dask job queue is actually submitting. So you see, if you've used an HP system, this probably looks familiar, where you have in this case it's just a bash. It's a batch script in which you have these comments that are actually specific to PBS that is telling the scheduler the configurations that you're looking for, and Dask job queue is going to submit a bunch of these. So you can also do the regular scale method. In this case, nothing happens because it's the same as what I had here. In cell 5, we're basically scaling in terms of workers, but we can also scale in terms of jobs. We can do adaptive scaling, pretty much anything that you would do with a regular Dask cluster. I wanted to show you the dashboard here, which basically will show you the activity of what's going on. Don't know why it's taking too long, but yeah, so that's mostly what we're going to talk about tomorrow. We touch on Dask Gateway, UCX, and a bunch of other things. So whenever you get time tomorrow, please come to the workshop. There's a bunch of other topics as well. I hope I didn't take
That's
too
awesome.
much time.
Thanks so much, Anderson. You're just bang on time as well. That was perfect.
Good.
Yeah, really looking forward to that workshop tomorrow. Like I said, I wanted to put all of that content into this workshop, and then I saw that you put one in, and I just thought, that's great. You go and do a whole like 2 hours on this, because there's so much to unpack in terms of HPC.
Sounds good.
So thank you very much. So next up, we have Brad here. I can see his camera's appeared. So I'm just going to hand directly over, Brad, if you want to take over the screen share. Brad's going to talk to you all about running Dask on top of a Hadoop cluster using Dask Yarn.
Thanks for the introduction. Let me figure out how to do that. Screen share. Oh, it's the big button right in front of me. Let's see.
Perfect. That's it. I can see that.
Okay. Cool. Well, thanks so much for having me. So I'll just briefly introduce myself. My name is Brad Miro. I'm a developer advocate with Google Cloud, where I focus the majority of my time on open source big data and machine learning. Recently, I've been spending a lot of time playing around with Dask and Dask Yarn and building out some of our integrations into Google Cloud Platform itself. So today, I'm going to tell you a bit about Dask Yarn, how you can get started with it, what it is, and why it may or may not be the right solution for you. So just to briefly go over the agenda, we're going to start by talking about just what Hadoop Yarn is there's a misspelling there. What Hadoop Yarn is, what Dask Yarn is, Dask and Spark, as well as getting started with Dask Yarn. And we'll go over the API and just some ways that you can get started with it today. So with that, we'll just dive right into Hadoop and Yarn. So just to give you, I guess, a brief history of where Hadoop and Yarn came to be in terms of data processing. So one of the, I would say, the beginning of the big data boom really happened in 2004 with the introduction of MapReduce, which allowed you to do distributed data processing across multiple machines with the MapReduce paradigm. In 2006, Hadoop was introduced, and this introduced the ability to have a distributed file storage system. There's actually a tool called HDFS, which is commonly used and used with MapReduce as well. These worked great for several years, but then one of the problems with using this model was the ability to really scale it, especially at the pace that big data was growing within the community. So that's where Hadoop Yarn came into play. And Yarn specifically is a tool for helping you do resource management across your Hadoop cluster. Continuing on with data processing, another large breakthrough was in 2014 with Apache Spark. Spark's 1.0 release happened then, and it's still widely used today. The 3.0 release actually happened last year, and it's one of the most popular big data processing tools just in industry. And then just to give you some context, of then Dask was introduced in 2018. So Spark itself is a little older than Dask, and we'll talk about, for those of you who may be familiar with Spark or the Hadoop ecosystem, I'm going to tell you a bit about why you might want to choose one over the other. Okay, but the talk is about Dask Yarn, so let's start to introduce that. So Yarn stands for yet another resource manager. As mentioned in the previous slide, it was introduced in 2012, so it's just around 9 years old now. The big breakthrough with it was the ability to actually separate your resource and application management. It was created to support, again, the Hadoop data processing and storage systems, but it's used for non-Hadoop applications as well for tools such as Dask Yarn. So this is located on the Apache Hadoop website. So just to give you an idea of how this model works, you can see in the middle here, we have this resource manager, which would be on the master node. So Hadoop and Yarn use a master worker model. So generally, you have this resource manager that's distributing resources across the cluster, telling which one of the applications can use, which machines, which resources. And then you might be able to see on this middle worker on the right, there's an application master. And so that's going to actually be distributing the workloads to the different clusters, the different machines on the cluster via containers. Now, the ecosystem itself is quite broad, and this doesn't even cover what's in the Hadoop ecosystem. But I just covered some of the popular ones that are being used today. So of course we have Spark, we have Rapids, which I know you're going to be hearing all about throughout the weekend. It's another great tool that utilizes different tools in the Hadoop ecosystem, as well as Dask. Hadoop itself is written in Java, so there's a lot of Java projects. There's Scala projects. There's Presto, which is a tool for being able to access different types of data that aren't necessarily based on your Hadoop in your Hadoop cluster. There's Hive, there's Pig, lots of great tools. Then Jupyter, of course, while not specifically a Hadoop tool, you can access and run workloads on top of your Hadoop cluster using Jupyter. So that's another popular one for interacting with it. Okay, so that's just a brief introduction to Hadoop and Yarn. So let's now talk about Dask Yarn. So Dask Yarn is a scheme-based tool for deploying Dask on a Yarn Hadoop Yarn cluster. And so Scheme itself is another tool that lets you run Python-based applications on top of a Hadoop Yarn cluster. And so Dask Yarn is utilizes that underneath the hood. Similar to other Yarn applications, Yarn handles the resource management for Dask Yarn, so you don't have to maintain that yourself, or Dask doesn't have to rely on it itself either. It introduces this object called the Yarn cluster object, which lets you interact with the cluster instead of using something like a local cluster or a CUDA cluster. This functionality is maintained in different ways, but the way that you would interact with the Yarn cluster is using this. Dask Yarn itself contains a Python interface for starting, scaling, and stopping Dask clusters, and it also has a CLI tool that is available to it. So the majority of the functionality is carried over from the from Dask core. So if you're migrating Dask code from, let's say, your local machine or somewhere else, the code changes should be fairly minimal. You should be able to just change the actual cluster object itself to be a yarn cluster. So you're able to use your arrays, your data frames, machine learning, whatever it is that you're using Dask for, you should be able to maintain most of that. And I mentioned GPUs earlier. So there is the ability to maintain the ability to use GPUs and tools such as Rapids using the Dask CUDA worker, which allows you to do efficient GPU utilization. And I know several folks on this call have either contributed or maintained it or have used it before. And then you can also use Kerberos on your Dask Yarn cluster using a tool called Kinit. Okay, it's a little bit about Dask Yarn. Now I want to talk a bit about why you might use Dask over Spark, since Spark is another fairly popular tool that's used with the Hadoop ecosystem. So just to give a very brief overview of what Spark is, it's an open source unified analytics engine for large scale data processing, fairly similar to Dask. It really was, the big breakthrough was that it allowed you to do this data processing in memory. It also has a rich ecosystem with various tools built on top of it for natural language processing, for SQL queries, graph algorithms, machine learning, lots of different tools. And it has APIs available in 4 languages, Python, Java, Scala, and R. So let's start with where they overlap. So the idea behind both of them is the ability to do distributed data processing. They both do that super well. They both contain APIs in Python, Python being the main language for Dask and an option for Spark. They both contain large ecosystems of partner tools. And again, you're going to hear all about different Dask tools this weekend. You heard about some just now. You're going to continue to hear about more. They're both wildly popular. We are at the Dask Summit, of course. And then, I can tell you that Spark is also, one of the most popular tools in the industry today. And they both support machine learning and the ability to accelerate your workloads using GPUs. So this is where they overlap. And now let's just talk a little bit about where they may differ. So the first one is that Spark gives you 4 options for programming languages. And I don't necessarily say this as a pro or a con, just as a fact. You can use, again, Python, Scala, Java, or R. I would say these are about in descending order of popularity, Python being the most popular today, I believe, where Dask is just Python. So if you are, if you use Python and it's your most, the language you're most familiar with, then, that might be a great reason to just stick with Dask. Another thing with Spark is that the set of APIs that it uses are totally new. So there is a bit more of a learning curve when starting to learn Spark as compared to Dask, where Dask, the APIs are deliberately designed with other popular Python data science frameworks in mind, such as Pandas and NumPy. So the learning curve there may be slightly less since the APIs should look fairly similar to you. Spark in and of itself is just older and it's more widely adopted today. I know that gap is closing, but today Spark, I believe, is still the more popular framework. And so with that, if you have, if you have questions or, if you're trying to debug, there's the argument to be made that there just might be more information available with Spark, given that it's just older and still popular. Spark is also underneath the hood based on Scala and Java, and it runs on top of the JVM. So with that, when you're debugging or configuring, there is a sense of Java knowledge that you should have when when working with Spark. You don't need that with Dask. You just apart from doing some aspects of contributing to it, you just need to know Python. And especially with using Dask on a day-to-day, you really just need to be familiar with Python. So there's the difference there, especially if you have no Java or Scala experience prior. Dask is a bit lower level, and since it doesn't run on top of the JVM, it's a little easier to just get started with, and then it's also better for high performance computing. You just heard that there's going to be a workshop tomorrow on it. You should definitely go check it out. So Dask is really great for that. Dask is also much easier to scale off of a local machine. There's clear benefits to just using Dask on your laptop. There aren't necessarily as much with Spark. It's really just designed to be used across multiple machines. And then last but not least, so with Spark, there's a lot of different configuration options available to you, which can be a bit daunting in terms of which knobs you should be tuning for the resource management, for workers, memory, what have you. Lots of different options here. Dask, there's just less so, and in my opinion, it's a bit easier to just get started out the gates in terms of fine-tuning your configuration. Okay. So how do you get started with Dask Yarn? So let's say you have a Hadoop cluster, a Yarn cluster. To get started, you can just install it. It's available both on Conda, Forge, and PyPy. So, whichever one works better for you, you can install it. And then there's two ways to actually implement it into your applications. So the first is to package it via either Conda Pack or virtual MPack, or the MPack, I suppose. And what you're able to do, and I'll show you an example of this in an upcoming slide, is that you can just provide that packaged Python environment to your Yarn cluster object, and it'll actually distribute that across the cluster. So that's one option available to you, or you can just install it on every node of the cluster. That's a little trickier to do because you have to make sure that the Python environments on each one are aligned, but that is an option for you to do as well. Now, in terms of configuring Dask Yarn, you do have a lot of flexibility in terms of configurations. I've actually just here taken a screenshot of the defaults that are available to you. The nice thing about this is that there's two ways you can provide these configurations to Dask Yarn. So the first is via a YAML file that Dask is able to locate and then can just read from. And so here, this is the default. These are the defaults here that it would read from. You can also create your own and customize this how you see fit. Or you can provide these inline when you're actually creating the cluster within your Python code itself. So you can see here, there are a lot of options for configuration. You can configure the number of Dask workers, the amount of memory, the amount of cores that are provided. You also have the ability in terms of like the worker, you can change the worker class. So if you have GPUs on your Yarn cluster, you can enable the Dask CUDA worker here. You can also provide the location of your zipped Python environment if you don't want to necessarily rely on the Python environment in your default Python environment, I suppose. And then you also have access to specific scheme configuration, which you can provide here. It's actually shown at the top of the Yarn file. So in my personal experience with using Dask Yarn, I haven't had to rely on this a whole lot, but it is available if there are more fine-tuned features that you may need. So now we talked about setting up Dask Yarn, but how about just Hadoop Yarn? If you don't have a cluster already, how can you get started with one? So there's a couple ways. So the first is you can get a bunch of physical computers, connect them all together and install Hadoop and configure the cluster to work together locally. Or you can get started with a cloud provider and use a managed Hadoop Yarn service. I know we're going to hear more about these generally later on in the workshop, but since I hail from Google Cloud, I'm going to talk about how we do it very briefly. And so we have a service called Dataproc. And Dataproc is Google Cloud Platform's fully managed Apache Spark and Apache Hadoop service. I've spent several years working on this product. I'm very biased, but I think it's great at what it does. It has the ability to create clusters rapidly in 90 seconds or less. You have the ability to get started with all sorts of different open source tools. I showed you a long list in the beginning of the talk, but there's even more than these. These are all available to just customize on the cluster, including, of course, Dask Yarn. When you're creating a machine, a cluster, you have the ability to configure the number of machines. You have the ability to configure the amount of RAM, the amount of GPUs. You have that fine-tuned customization available to you. And Dataproc is also ephemeral in nature. So you can create a cluster just for what you need it to do. You can then shut it down since you have access to that rapid cluster creation. It's really nice to be able to use this just for the specific workloads that you would like, especially if you want to just test around with Dask Yarn, you have the ability to do that on an ephemeral cluster. And then last but certainly not least, Dataproc is part of the larger GCP ecosystem, so you have access to all of the other great services that GCP provides, including BigQuery, which is our data warehouse, and Google Cloud Storage, which is our blob store. And we have open source connectors specifically for these two services to work with Dataproc and Spark and the like. So if you want to get started, this is just a sample G-Cloud. So we have an SDK for getting started with GCP. So here I just have an example command of how you can create a cluster. I have here highlighted the open source installation script that we provided for Dask and Dask Yarn. So if you want to get started with this, you can check it out here and create a cluster. This one in particular would also create a Jupyter notebook environment on top of your cluster so that you can interact with it in Jupyter. Okay, and then to talk a little bit about some of the actual features of Dask Yarn and the APIs and some of the UIs that are available to you. So here, this is just from the quick start on the Dask Yarn website. This is how you can create a yarn cluster object. So here you can see that we provided, the quick start provides some just basic config. In this case, it points to the location of the Python environment, provides some configuration for the amount of cores and the amount of memory. You don't have to include these if they're bundled in the default configuration, or excuse me, in a YAML file, or if you just want to rely on what's in the defaults, you can do that. So for instance, on Dataproc, we've actually tuned the defaults a little bit so that you don't have to provide any of this out of the box just to get started with it. You can provide an open or an empty yarn cluster object, and it should work. But then you also have the ability to configure this, as you see fit for your workloads. And then just like you would use Dask distributed, you can provide the cluster to a client object. And then also with Dask Yarn, you can shut down either one of these. And it's very, should be a very similar experience to using any other, Dask object or Dask cluster. Okay. A common feature of using Dask is you can, in a Jupyter notebook, you have access to, viewing data about the different objects that are provided for you. As you're using Dask in a notebook. So here, you can get information about an array that you have created. This functionality is maintained. But something that is unique to Dask Yarn is actually the ability to manage and scale the cluster from within a Jupyter notebook. So there's two ways you can do it, or I guess there's a couple ways you can do it. But the Yarn cluster you can scale manually, and you can say how many Dask workers you'd like your your cluster to have, or you can do it dynamically. And so there are APIs. There's API functionality built into Python for this, but you can also do this within the Jupyter notebook itself. So these both contain drop-down menus, and you can say how many workers you want. You can also enable or disable adaptive scaling. Really nice feature, especially if you're going to be doing workloads in using your notebook. You have nice control over this via a GUI. And then since this is a tool that's built on top of Skein, you also have access to the Skein web UI, which is available for all different Skein applications. So here you just have some more information that talks about, or shows you some information about different processes that are running, the status of your Dask workers, the runtime, how long certain jobs have taken. Really nice tool for being able to just further debug and monitor your Dask Yarn workloads. So that's all I have to share today. If you want to learn more about this awesome project, you can go to yarn.dask.org. If you have questions for me, I think I have a couple minutes, but I'll stick around. We can answer them in the chat. And then also my Twitter handle here at Brad Miro. Feel free to send me a message, and I'm happy to chat. Thanks so much.
Thanks, Brad. That was an excellent talk. We definitely have 5 minutes for questions if anybody has some. We've got one in the chat here, which says, we cut this yarn cluster creation into the Dataproc instance and then talk to it from a Jupyter Hub notebook. Any suggestions to streamline this workflow?
We cat this yarn cluster creation to the Dataproc instance and talk to it. I'm not sure I entirely understand the question, but if you're looking to use Dask from Jupyter Notebook, it's available. You would set up both of them how you would Jupyter Notebook generally, how you would set up Dask or Dask Yarn, and then this is just available to you. Now there is some extra setup if you wanted to use something such as the Jupyter Lab extension, but you otherwise have access to all of that as well as the different web UIs that I talked about here.
Great, thanks. Is there any more questions for Brad? Feel free to throw them in the chat. Wow, we're going to head over to the I keep forgetting what it's called now, the GatherTown chat thing at the end. So if anybody has any more questions, I think Brad has agreed to join us there. We're halfway through the workshop now, so thank you, Brad, for that presentation. I think what I might do, we've got like a couple of minutes in hand. It might be good to have like a rest break just for a couple of minutes, being halfway through the 2-hour block. So we'll resume this session at 5 minutes past, which is only in a few minutes time, but please feel free to go and refill your water bottle or something. Oh, another question has actually popped just in. Can you control the cluster size and the instance count from Jupyter?
Yeah, so you can control the number of Dask workers across the cluster. What you have less control over is the size of the yarn cluster itself in terms of physical machines. Those you would have to either do in the Dataproc console, or you can interact with, let's say, the Dataproc or yarn service using, let's say, like a client library. But in terms of what you have out of the box would just be the ability to scale the Dask cluster itself.
Great. Thank you very much. Okay, great. If there's not any more, yeah, Brad, if you don't mind letting go of the screen share, so I can take that back over, that'd be excellent. Thank you very much. Thank you again for that talk. It was excellent. So let me get my screen share set up, ready for the next talk. But we'll be back in 2 minutes just to have a quick break here. Okay, I think I'm going to pick things back up again. We're kind of back on schedule again. We've gained a little bit of time there. So the next talk in this workshop is going to be about deploying Dask clusters kind of natively onto various cloud platforms. I'm going to start by doing a little bit of this as I happen to be the author of this library. I'm going to do a very brief intro, but then I'm going to hand over to my colleague Nanthini from Rapids at NVIDIA to talk about like a specific use case of this on Azure. So as we talked about cluster managers before, within the Dask ecosystem, we have a package called Dask Cloud Provider, and that is like a whole bunch of cluster managers that allow you to construct and manage ephemeral Dask clusters on like a whole bunch of different cloud platforms. Now, these cluster managers are kind of implemented in a whole bunch of different ways. The idea is for them to feel kind of as native to each cloud as possible, right? And each cloud has got its own differences and its own nuances, and so things do like differ slightly. But the idea is that you should be able to reach into that cloud, grab some resource by whatever means that they have available. For some clouds, we have more than one approach, depending on your preferences. Say you're an AWS user, maybe you like to use containers on ECS. We have a cluster manager for that. Maybe you prefer to use VMs with EC2. We have a cluster manager for that. Maybe you want to use kind of more serverless containers with Fargate. We have a cluster manager for that, right? We have a whole bunch of different things. We're very, very open to contributions. If there's a platform or service that you want to deploy a Dask cluster onto that we don't already support, we've kind of built scaffolding within Dask Cloud Provider for hopefully implementing those things reasonably easily. So just a very quick snapshot of code from the GCP implementation that we have. You import the cluster manager as you do before. You instantiate that cluster manager. You get some feedback about what's going on, right? Sometimes these launches can take a few minutes to get these resources in the cloud, so you get a bit of output back. But then you can pass that cluster manager straight through to a client, connect to it as you would any Dask cluster, and now you're leveraging this cloud resource. So as I said, we try to give our integration with each cloud as native a feeling as possible. We want to try and have as small amount of requirement as possible for each user. So if you want to use Azure, you just need a subscription and an API key, and you should be able to get going. And we want to have support on all, we have support on the big 3 cloud providers, but we kind of want to have support on all kind of major clouds. So I'm now going to hand over to Nanthini. If you let me stop sharing my screen, you can take over, and please tell us the rest of the presentation.
Can you see my screen now? Awesome.
Yeah, I can see that.
So I'm Nanthini. I'm working with NVIDIA as a data scientist, and I work with the Rapids team. So I'll be talking about this particular use case of deploying a multi-node, multi-GPU model on Azure using the Dask cloud provider. A little bit about what Rapids is. I'm sure you'll hear about it throughout the workshop as well. We're basically accelerating for GPUs. We're adding GPU optimized libraries for machine learning processes. And QML is basically the machine learning library for within the set of libraries that we provide. And it's a very easy to use. It mimics the scikit-learn interface. So you just have to swap out like the import statements, and you're mostly set to run things on the GPU if you have that available. And the good thing about QML is it provides an integration with Dask, which allows for Dask to run the distributed and process the GPU data frames in a distributed fashion, like it would pandas data frames. So this is just a basic like understanding of why we need Rapids. These are kind of the numbers from like the CPU versus the GPU. You can see that the speedups are nearly like 50x in some cases. This just means the things that you would wait for a couple of days for it to finish running might just happen within like a lunch break, which makes it easier to experiment and stuff. So that's kind of where Rapids comes in. So let's talk about the experiment itself. We're going to be running a random forest model on a multi-node, multi-GPU setup on Azure Cloud for a regression task using the NYC taxi dataset. This is the setup for the local environment. You need Rapids installed, which can be done with Conda or from the source or from Docker container, which is what we'll be using. We'll use the Docker container to run whatever packages that we need. And we need the Dask cloud provider. This is for the Azure VM setup itself. This is what's going to be managing. This is the cluster we're going to pass into the Dask client. And Azure CLI is just for the CLI interface for Azure. You can also do this same on the portal as well. And Azure OpenML datasets, that's where the dataset itself is going to be coming from. So this is kind of what we need in the overview. And there's an attached notebook to this. So all of these packages are installed within that notebook too. And this is kind of the setup. So we need a resource group, a virtual network, and a security group that provides access to the Dask scheduler and the Dask dashboard, which we can now access from the cluster itself. So this is kind of the setup, and make sure they're all in the same location so that there's no conflict within Azure. Let's talk about the cluster creation now. As you can see, we have like a bunch of these, the resource groups that we've set up, and we specify the VM sizes. Since we'll be running on GPUs, we want a VM that supports GPU. So any VM that supports GPU would work. In this case, we're going to be using the 12SV3, which is 2 V100s. And we set the worker class to make use of the GPUs that are in the system as well, which is the CUDA workers. And the number of nodes in this case will be 2. We'll basically have 2 VMs set up. As you can see here, we have 2 Dask workers that will have 2 GPUs on each of them. And this is kind of what you'll see when you run that cell for cluster creation. You'll get an IP address with where the scheduler will be running. And once the client is set up, you can access the dashboard using 8787 port. And this is similar to what you would set up for any of the Dask clients, where you just pass in the cluster and then you wait for it to scale up. And as you can see that we're waiting for 4 of the workers to scale up because there's going to be 2 nodes and 2 GPUs across all of them. That's what this step does. So once we're done, okay, this is the background about the data set. So what problem are we trying to solve? I'm sure like most of you have seen or like used the taxi data set. It's basically a regression task to predict the fare amount given like a bunch of parameters like pickup time, pickup date, and like the number of passengers, the payment type, the distances involved within the New York city limits. So that's the task we're going to be solving. We're going to be predicting the fare amount for the trip given all of these parameters. And like I said, the data set is going to come from open data sets from Azure. It's just a very clean way to read it. You just have to pass in the start date and the end date, as you can see in this API. And this is going to read the yellow taxi particularly. And they have the other colors as well. So it's very easy to read into pandas. You just have to convert it into a pandas data frame. And now we've loaded it into the CPU. And this is the last line is where the GPU loading happens, where QDF is the package from the Rapids library. So we now load the CPU data frame into GPUs. And from there, the Dask QDF is going to be the Dask distribution of the QDF data frame itself. So the main difference is, instead of distributing pandas data frame, this is going to be distributing the QDF data frame. So that's the difference between the normal Dask data frame versus the Dask QDF data frame. And these are like some of the steps that we are going to be doing within the workflow itself. This could be anything for different workflows. It's a bunch of pre-processing, like making sure we have the correct data types, the correct, we drop out null, and we add like a few features like splitting the date time column to get like more information from them, and cleaning it up and adding like the Haver sign distance as well, so that we can estimate that, add another distance metric to it too. So this should be similar to what you've seen in most workflows. Going into the actual random forest model, this again should be very similar to like a CPU-based workflow where you've seen like a random forest model being defined and then training it on something and then predicting it on the test set. The only thing that might be interesting is the persist across workers, which is coming from the QML library. This is very similar to calling Dask data frame dot persist. It's just an easier way to call like on all of them at once. So that's what this is doing. So the persist helps all the workers have access to the data set they're going to be dealing with, so that we don't get like no data errors, or like those can break the workflow too. So as you can see, the code itself is very similar to what you would see on a CPU data frame, CPU workflow. So it's going to be pretty much the same. The API is very similar and like very easy to understand. And this is where like it makes it easy to just run the multi-node multi-GPU model. And this is the dashboard that we get when we go into the IP 8787. As you can see, there are 4 workers. As I said, it's going to be across 2 different machines, 2 different nodes. Each of them are like 2 GPUs. So this is what's happening behind the scenes. And that brings us to the end of the example, which was pretty straightforward to set up, and like a few lines of code to set it up before, and like just setting up the cluster and getting Azure environment set up. You can run a multi-node multi-GPU model, pretty straightforward. And Dask Cloud Provider makes it super easy to run it. I just showed you the example on Azure. You can run it on AWS, GCP, and other clouds too. And Rapids, we're using the QML Rapids random forest class regressor, but you can obviously swap it out with like an XGBoost MNMG model as well. That would work too. But Rapids just provides a very easier way to integrate like a very CPU looking workflow into the GPUs. Both of these libraries are under development right now, so expect some issues along the way, and please let us know how we can make it better to improve the experience for you, and hopefully get it into a much more fine-tuned and a stable form. The notebook that I just spoke about is available in the Rapids GitHub repository within the Cloud ML examples. You should be able to see that, and like the instructions are within the notebook as well to run through. The reason we didn't do a live demo is because the resources might not necessarily be available on Azure, and we don't want to wait for too long, and we had like a time constraint. So yeah, that brings us to the end of the talk. Hopefully this was helpful in getting you excited about Dask Cloud Provider, and hopefully try it out and see like how you can use it in your own workflows.
Nanthini, that was a really good talk. Hopefully everybody found that interesting. We've got a couple of minutes left. So does anybody have any questions? We did have one in the chat, which I did answer, which is just kind of asking about why why did we choose a VM here that had 2 GPUs, and why do we have like a one-to-one mapping for workers and GPUs? I don't know if you want to answer that a bit.
The reason we chose with 2 GPUs is because we wanted to show the multi-GPU aspect of the run itself. Because QML Dask kind of makes use of that. And one-to-one mapping is mostly, right now, I think that's the most stable form that we support. And we don't want to scale it up even further than that. But this is just like an introduction to like multi-node, multi-GPU runs. Hopefully it gets better with like, as we spend more time developing the API itself.
Perfect, thanks. There any more questions in the chat? Just give it another minute or so. In the meantime, as I said, we're kind of actively developing Dask Cloud Provider at the moment. There's a bunch of work going onto it. The support now, kind of towards the end of last year for the 3 major clouds, and but like there's a whole bunch of other systems that you might want to deploy onto, right? Like we support containers on AWS and we support VMs on all the others, but we don't yet, support containers directly on Google Cloud or anything like that. We kind of want feedback from the community and to hear, like, where are you deploying things? Do you have constraints as organizations about which services you can use? How do you want to run things on the cloud, so that we can kind of focus our efforts there? So if you have any thoughts about that, please head over to the Dask Cloud Provider GitHub repo, raise an issue, let us know, chat to us on the Dask Slack. We're very keen to hear all the feedback that you might have. So the last talk of this session now, we're kind of coming up to that time. So I would like to invite the 2 speakers for this session to appear. I haven't actually had a look in the chat to see if you're here, but Adam and Amit, are you around?
Yeah, we are. Should I go ahead and share my screen?
Yeah, please do take over the screen share.
Great. All right, and we're ready to get started.
Yeah, please do. So I'll just quickly introduce you. This is Amit and Adam from Quantsite, here to talk to you about deploying JupyterHub and Dask Gateway on Kubernetes using QHub. So yeah, please take it away.
Thanks, Jacob. So yeah, I'm Adam Lewis. I'm here with Amit Kumar. We are QHub core maintainers at Quantsite. And just as a side note, we are hiring, and some of these roles pertain to contributing directly to Dask. So if that interests you, definitely check out our jobs board. But yeah, we're going to talk to you today about QHub and how QHub can help you deploy JupyterHub with Dask Gateway on Kubernetes in 15 minutes. Okay. Well, all right. And so as part of that, I want to actually deploy QHub in this presentation. So I'm going to get it started early, kind of before we tell you more about it, just so that we have time to see it actually deploy. So first I'll install QHub from pip install QHub. And then I'm going to export some environment variables that I have stored in my .env file. And these are just a few credentials from the cloud provider we're going to use. And I'll talk more about that later as well. And then I need to create a config file. And so this is a rather long command, but we're specifying, it's because there's a lot of customizability. So we're able to specify what cloud provider we want to use here, and as well as the domain that QHub is going to appear at later, and the GitHub repository that we want to be created as well. And so I created my init file or my config file a little bit earlier, so I didn't overwrite it, but it's very quick. And I just did that because I didn't want to have to make a small edit to add myself as a user there during this. But I'll show you the details of that later. And then so after you've created your config file, then you can go ahead and deploy. So just run this QHub deploy, specify your config file that you've created, and then your DNS provider if you choose to specify that. Okay, so it's off and running. And Terraform is provisioning all the resources, setting up QHub behind the scenes. So we'll check on this in about 15 minutes, and we'll see how it's doing. And in the meantime, Amit and I are going to tell you a little bit more about who we are And then we haven't shown you, too much about QHub. So we're going to give you a nice demo that'll show you some of the nice features of QHub, including Dask Gateway and how you can deploy Dask cluster easily. And we'll talk about QHub under the hood. And then we'll go back to this deployment that I just kicked off and make sure that it deployed and check how long it took. And then we'll summarize and finish up. So who am I? I'm Adam Lewis, and my background is in chemical engineering, but I found that I enjoy data science and software development more. So I am a data scientist at Quansight at the moment, and also a core developer of QHub. I'm in the Austin area, and I enjoy getting out and about in the state parks in the area. So here I am with my wife last weekend at one of the nice state parks around. Also, here is my contact information. I'm most active on LinkedIn, and I'd love to connect with all of you. So feel free to reach out there. All right, and then Amit can't hear you quite yet. There you go.
Can you hear me now?
Yeah, we can.
I'm a software engineer as well. Thanks, Adam, of that deploy that thing to see in does he also to the queue and open source. I mean, I will supporter that on site. I'm also
Amit, I'm getting a lot of kind of distortion and stuff on your microphone. I don't know whether you might want to restart your Zoom connection or something. It's pretty tricky to understand what you're saying. I'm afraid technology's letting us down.
Yeah, I'll message him. Okay. So yeah, my co-presenter is Amit Kumar, software engineer at Quansight. And he's a core developer of QHub. And he's open source enthusiast, as it says here. He's also a creator of CIRun.io, which allows you to run GitHub Actions on the cloud. And we can see his Twitter handle and GitHub handle here, and I'm sure he'd love for you to reach out as well.
Can you hear me now?
Yeah, there we go.
Okay, thanks. Sorry for the connection delays. So Quansight I was talking about Quansight is a consulting company in the space of data science and data engineering, and we believe in making open source sustainable, and that's our mission. So QHub is one of the brainchild of that mission. So that's why we are here to talk about QHub. So it was all started by Travis. Travis Oliphant is a well-known personality in the open source, and he is also the creator of NumPy, SciPy, and also author of Numba. So thanks, Adam, for kicking off that deploy right away at the start, so that we can see by the end of it how it looks like. So meanwhile, I'll show you a bunch of QHub features. I'll share my screen in a second. See my screen, all right?
Not quite, not yet. Okay, here it is. Yeah.
So this is how the QHub would look like when it is deployed. So I'm starting from the scratch. So you'll sign up with a auth provider. So we have support for a bunch of auth providers, and Auth0 is one of them. The reason we chose Auth0 for this purpose because it is quite flexible and supports multiple authentication mechanisms. You can use GitHub as well. So that's the bunch of tools you can in the Adam initially used to deploy QHub. So I'm going to choose the large GPU instance, which is 8 cores and 32 gigs of RAM with one NVIDIA Tesla T4. So we'll show you the notebook in a sec with a bunch of small examples to like a sneak of QHub. The actual QHub, the one we promised to deploy in 15 minutes, is getting deployed. And meanwhile, this is deploying. I'll show you the QHub docs in a sec. So this is how the QHub docs look like. The example I was thinking about is so of things you configure, and all of them be configured with like YAML file. So my a bit floppy for that.
I'm really sorry, but you seem to be cutting in and out again. I wonder if it's worth turning off your camera just to maybe conserve a bit of bandwidth, having the screen share on as well.
Okay, makes sense. Okay, is that any better now?
Yeah, that sounds better.
Okay, so I think the GitHub is the notebook should be loading in a few seconds. And
let's see, did we lose Amit? We may have.
Yeah, it seems like he dropped off.
All right, let me pull it up in the meantime. Okay. All right, so let's do my best here. So yeah, the nice thing about QHub is I like to think of it as like a Jupyter hub on with like batteries included, Jupyter hub. So here you're able to specify like how many resources you want, and these are configurable in that in an init file. And so I'll go ahead and spin up a worker here. Maybe I already have one up. Let's see. I think this is old. Yeah. So let's see. So while that's spinning up, let me show you the dashboards feature. So this is a Jupyter hub on steroids. So it has a lot of like external integrations built into it. And so one of the nice things is you're able to share your dashboard with others. And so here I have a dashboard that I've created earlier, but I'll just show you the creation process. You can specify the name of the dashboard. You can specify what users you want to share it with. And you can also, there's, various dashboard frameworks in the Python ecosystem, Voila, Streamlit, Plotly Dash, Boca, RShiny. So it supports all of those. And then we can also specify what conda environment we need to run that app. And then here we have the entry point for this particular app. And then after we save it, we can specify, what size of instance does it need to be able to run. And then once that spins up, we're able to see a dashboard. And so while that's spinning up, I'll show you, we can see other dashboards that other people have shared as well. So it makes it really easy to share dashboards with others. And you can also share just a URL in order to access the dashboard. Again, so this is running on a cloud provider. And so we've got to wait for some of the resources to spin up here, which is what's happening. We're on GCP, and we're probably scaling up to another node here. Additionally, let's see if this has spun up. Okay. So this node is also spinning up here. Let's see what we can do. Probably because Amit and I are both spinning up at the same time. So in the meanwhile, while this is spinning up, let me continue on with the presentation. Then we'll come back to the demo in just a little bit. All right, so yeah, like I mentioned, I like to think of Jupyter or QHub as a batteries included Jupyter hub. So we saw some of the Jupyter Lab and Jupyter Hub integration, as well as we will see Dask Gateway integration. Also, we have support for GPUs. And one of the nice things is that we have full support for Linux user and group permissions. And then we also integrate with quite a few other libraries and other projects. So Contain DS Dashboards is that dashboarding package that I showed you. We also have integration with Prefect. You can also do a video chat just from directly within QHub. And then we're adding more features regularly. And then I will also mention that most of this talk is going to talk about QHub Cloud, but also we have a QHub on HPC, which is a Jupyter Hub on a HPC, and in particular Slurm system that works as well. Okay, great. So here we can see we've booted up our Jupyter Lab instance, and also here's our dashboard that we were loading before the instance has spun up. And so let's talk about the dashboarding situation first. And so, yeah, so once the node is up, that initial spin up takes a little bit of time, but once it's up, you can access it very quickly, and you can share it with whoever you want to. So it's a really nice integrated solution to sharing dashboards that we have built into QHub. Okay, so another thing I want to show is the GPU support. And so I spun up a pod on a GPU instance. And so you can see that if we run NVIDIA SMI, we can see that we have a Tesla K80 GPU available. And just to prove that we can do some computation, let's go ahead and run this matrix multiplication. And we're using the CUDA, Numba CUDA decorators in order to run this on the GPU. All right, so we've got our GPU support that we're showing there. And then also here's, one of the main features of QHub, right, is that we're able to spin up a Dask cluster. And so very easily. So we can do this fixed size cluster by specifying the number of workers right here. We also have access to, the adaptive clusters that some of the other speakers have mentioned as well. And I will mention it does take, a minute or two to spin up some of the nodes for the cloud providers, spin up some of the nodes that we're using, right? So we can get more compute. But once you've spun up the nodes, then you're able to adapt your workers very easily. You're able to scale up and down your workers very easily. So I'll see. So we've already spun up to our worker here. All right. And then also one last thing I wanted to show is we're able to do this pairwise distance calculation, and here's a little bit showing the full Unix permissioning that we have available as well. So right here we can see the various users and that they're all users on the QHub system. They have Linux permissions, as I've mentioned earlier. A few other nice things I wanted to show is that there's this built-in video chat system within Jupyter Hub now, and within QHub that comes by default. And I actually haven't had an opportunity to use this myself, but anyway, it's using Jupyter Video Chat, I believe, under the hood, and so you can create. I imagine we can create a new room here. Right, and then it's powered by Jitsi. All right, so I won't actually do that because I don't want to mess up our Zoom call here. But let's go ahead and move on. Oh, here we go. I'll just block that. Okay, so another thing that we wanted to point out is we also have integration with VS Code and code server. So we can go ahead and access those same files through a VS Code interface. So we can, have all the benefits of doing that as well. So it's really nice integration with this VS Code IDE. All right. Okay, so I think that was most of the features that we wanted to show. So let's go and proceed with the presentation. So yeah, we saw Jupyter Lab, we saw Dask Gateway. We're able to spin it up very easily. We have GPU support, Linux permissions, and Jupyter Video Chat. We saw the dashboarding, and I didn't show Prefect, but also has integration with Prefect, which is a workflow automation software. And we're adding more features all the time. So now let's switch gears and talk about QHub under the hood. Okay, so there's a lot going on in QHub under the hood. We're using Python to do that, to implement that CLI tool that we have. We also are using Terraform to specify, provision, and configure our infrastructure. And so we need to get that compute from somewhere. We're getting it from cloud providers in the case of QHub. And there's you can specify your own on-prem infrastructure using QHub HPC. But for QHub, this cloud version of QHub, we get our compute from the cloud providers. We support any of the major cloud providers listed here. And then what we're doing is we're provisioning a managed Kubernetes service through that cloud provider. And then we're using Helm to install some of these things that you've seen, such as the Prefect integration. ClearML integration is also going to be installed through Helm after that's integrated. And so perhaps the nicest thing, though, is this GitOps approach. And so I'll talk a little bit more about it, but we use GitHub actions to make managing your QHub really easy. And I'll show you that more in a second. And then authentication providers that we support right now are Auth0 and also password-based authentication, with additional authentication providers on the roadmap. So that was a lot that went into building QHub. But the great thing about it is that if you know GitHub and you feel comfortable generating API keys, you should have all it takes to deploy and maintain your own QHub deployment without the need for a dedicated DevOps team. Okay, and so I'll talk about what makes that possible. It's really just these 4 steps. So let's go into a little bit more detail on what those 4 steps were that I did at the beginning of the presentation to deploy QHub. So first, we need to store some credentials as environment variables. So I did have to log on to the Google Cloud console, create some Google credentials and a project, which I would fill in here. And then I created a GitHub token, and then you can fill in your GitHub username. And that's so that you can go ahead and automatically create the deploy step can automatically create a GitHub repo for you. And then these last 2 blocks are optional, but are nice. So you can specify your authentication provider and your DNS provider, as well as the credentials there. So once you've filled this in with your credentials, you can run the QHub init, which I did at the beginning. So it generates this rather large config file here, because there's a lot of customization you can do, but a lot of these values are defaults. So you don't necessarily need to edit most of this, but it does give you a lot of ability to customize as needed. So I'll point out a few particular parts of this QHub config file where everything is controlled. This is how you're going to manage your QHub in the future through this file here. Okay, so here's how we specify what users we want to be able to access our cluster. And so you can put the email address of the user. You could add more users below. And then also you can specify what the user ID. This is like Linux user ID and the Linux user groups that you're part of. And so that's how that's done. You can also customize QHub to the look and feel of QHub to match your own company logo and your own company's colors and scheme there. Additionally, a lot of these external integrations can be turned on and off through feature flags. So CDS dashboards can be enabled or disabled very easily just by changing this feature flag in the config file. So if you don't want it initially, but then later you decide you want to try it out, you can go ahead and change that very easily. And then here's where we're specifying what node types we want to use. So this particular example is on Google Cloud, although we support other cloud providers as well. And we're specifying, we want to use the N1 standard 2 instance types here, and we can specify our scaling limits as well. Here's how we specify what amount of resources we want to allow our users to use, and also our Dask workers. So we created 2 different profiles. We have a small instance resource profile, and then a medium instance resource profile if we want our users to be able to access, 1 CPU and 4 gigs, or 2 CPUs and 8 gigs for whatever workflow they happen to be working on at the time. And you can add additional ones here, allowing for additional CPUs, additional memory limits as needed. And then the same with the Dask workers. And then also you can specify your Conda environments that you'd like to have access to here in this file. And then they'll be available to all your users and all your Dask workers after you run your CI/CD, which I'll show you in just a second. So QHub deploy is the step that I ran that takes about 15 minutes, and that'll go ahead and set up your GitHub repo for you, and also your GitHub your QHub deployment for you. So I'll show you that in just a second, that on the one that I deployed at the beginning. And then I think this is probably the most important step, right, in managing your QHub going forwards. And so you're going to just make those edits to the QHub config file that I showed you a few slides ago. And also the QHub deploy is going to set up all these GitHub actions for you. And what that allows you to do is just use your regular Git workflows, pull requests and merging pull requests. And so after you edit that file and then make a pull request and merge it in, this will go ahead and the GitHub through GitHub Actions, you're able to automatically make the changes to your cluster that you've specified. So it makes it really easy to not have to mess with Kubernetes, not have to mess with Terraform. Just use your regular Git workflows that you're already familiar with to manage your QHub behind the scenes. All right, so now here's the moment of truth. And so I'll show you, it did complete successfully. It took about 744 seconds, which is around 13 or 14 minutes. And I think it's around 14 minutes. And then here we can, we didn't specify a certificate in this particular example in this QHub deployment. But that can be set up as well. So here I've loaded it. I've bypassed that security warning, but again, you can set up a certificate, SSL certificate, so you wouldn't see that and your users wouldn't see that very easily. But yeah, then you can go ahead and spin up your instance as well. So I think, yeah. So I think I've also, I may have not added my user there. There was that authentication bit that we were seeing. I didn't add my particular email to this deployment either. And so it was denying me access. But again, you just edit the QHub config file, and then that works right off the bat there. Okay, so to summarize, QHub allows you to easily set up a Dask cluster. It's a collaborative open source data science platform. And then you don't have to mess with Kubernetes or Terraform. You just use your typical Git workflows to manage that in the future. And so thanks for your time. Here's a few links over here. Particularly want to point out we have an active QHub Gitter channel. If you're interested, feel free to join that. And we'd love to collaborate with you further and communicate with you all further. Thanks.
That's great. Thank you very much. Thank you, Adam, for kind of picking up the presentation there. Too bad about Amit's internet connection. This is always the trouble with doing these kind of virtual conferences, right? Like you can't predict on those kind of outages.
Definitely.
So that was it. That was the kind of final talk within this session. There've been a few questions in the chat. I think we might take a question or two here, and then I'm going to kind of encourage everybody to head over to the Gather Town, and we'll go and kind of head into one of those kind of private spaces, and we can have kind of more of an informal chat. So if folks have got questions about how they, what their deployment problems are, how they're trying to deploy Dask, we can just kind of chat in less of a, this is very much like an us broadcasting to you scenario. So we'll head over to GatherTown to move to a bit more of a closer one, smaller one. So let's just head back through the chat and I can have a quick look. So a bunch of the questions are about standalone and on-premise deployment. So could you just say a little bit more about whether you've got that support in QHub today?
Yeah, so typically what we do right now is for cloud deployments, we use the QHub repo, and then we have cloud QHub HPC. So for on-prem deployments, we'll set up Slurm. And so several of our clients are using on-prem deployments. We'll set up Slurm, although you can set up a, so we set up Slurm on your in-house infrastructure, and then we use QHub HPC in order to deploy QHub with same type of thing that we've seen here, but using HPC under the hood instead of Kubernetes.
Great. Let me just have a look if there's any more conversations. There's a lot of folks just saying that it's great, which is good. But yeah, no, okay. I think okay. I think that's about it for questions in the chat there. So what I'm going to do is I'm going to mute and turn off my camera. I'm going to screen share just a slide just to remind folks where to find us on GatherTown. If everybody wants to kind of make their way over to that, you can head to the events page on the Summit website to kind of find a link through to there, or you can follow the one in the slide I'm about to put up. I'll head over to like a space in the town, and then yeah, feel free to join. Yes, that's a good question, Rich. Let me put that link. Oh, I've clicked it. I didn't mean to click it. Yeah, I'll do that, and then we'll head over there. So I'll see you over there in 2 minutes.